Hello everyone. In this video, we are going to discuss problem number 703 from test of mathematics at the level 10 plus 2. So the problem says that you have a function from set x to x such that when you double compose f, you get back the same element. And this happens for every x in the set x. Now, what we have to find out is that if the function is 1, 1 or on 2 or both or neither of them. So let's start by the 1, 1. So for 1, 1, what we should do is we should take that. Suppose there are two elements, that is x1 and x2, for which f of x1 is equal to f of x2. So then if we succeed in proving that x1 is equal to x2, then we are finally showing that there does not exist two distinct elements for which the functional values become equal. And now let's compose f on both the sides and look at the definition of f. This definition, what is given, that is, if we double compose, then we get back the same element. And so we get back here x1 and we get back there x2. And so we have proved that x1 and x2 are the same element. And that's why there does not exist two distinct elements for which the function takes the same value. Now, so that means this implies that it's 1 to 1. Now, what about the ontoness of the function? So as you can see, the function f is taking elements from the set x to the set x. So all these are the set x, and now the function f is taking elements from the set x to the set x, or it might be a subset of the set x. And now from there, from the range of f, again the function is acting upon all those elements in the range of f, and then it is again taking it to a subset of x or the whole of x. So that's what we have to decide. If the function is onto, then it's going to the it's mapping to the all of x, and if it's not onto, then it's mapping to a subset of x. And so now let's use again the property of the function that is given. Now suppose if I have an element in x1 such that there is no preimage. So I let me think that, okay, fine, there is no preimage for this x1. Okay. Now, as you can see that if you start with an element x1 here, then in the range you are going to get f of x1. And now again, when that is operated by f, you are going to get, so here you are going to get f of x1, and that is nothing but equal to x1. But x1 was an arbitrary element of the set x, right? And now you can see that there is a preimage of x1, which is nothing but f of x1. And f of x1 is an element of x. And so there is an element of x, that is f of x1, such that f, when operates on f of x1, that element in x, it gives you x1, right? And since x1 is an arbitrary element of the set x, so this is true for every element in the set x. And so the function is onto. And so the correct answer is f is 1, 1 as well as onto. So option C, both 1 1 and on 2. Now let's discuss the conceptual errors students might make while solving this question. The one oneness was fine, but while proving on to, students might think that since the function is going from the same set to the same set, and since it's 1 1, so it might be on to. But that is not the case. That is true only when the set X, its cardinality is finite. That is only true when the cardinality of the set X is finite. But if the cardinality of the set X is infinite, then it's not true. So let's see if we have a counter example in the case of infiniteness. So let's take, for example, the set of all natural numbers. So I have a mapping from the set of all natural numbers to the set of all natural numbers, and the mapping is defined as f of x is equal to 2x. And as you can see, it's linear, and so it's 1 1. But it's not onto, right? Because like 1 is going to 2, 2 is going to 4, but there is no inverse of this element 3. There is no preimage for this element 3 under the map F. And that's why it doesn't work while when your set has infinite cardinality. Okay, so that is only true when your set has finite cardinality, and then if it's 1 1, then obviously you can say that it's onto. So 1 to 1 implies onto for the finite case, but for infinite case this is not true. And we have seen an example here. Thanks for watching the video.